From the smallest atom to the largest galaxy, the universe is a vast and mysterious place. Its sheer scale is almost impossible to grasp, and yet it is in a state of constant change and evolution. We, as humans, have always looked up at the night sky in wonder, seeking to understand our place in the grand scheme of things. This is the story of our universe, a cosmic chronicle that spans billions of years, from the fiery birth of existence to the intricate dance of celestial objects. It's a tale of creation, destruction and renewal on a scale that defies imagination. We'll journey through time and space, exploring the key events that have shaped our universe into the awe-inspiring spectacle we see today. Prepare to be humbled by the sheer magnitude of the cosmos and inspired by the elegance of the laws that govern it. From the formation of the first stars to the birth of our own solar system, every chapter in this epic saga is filled with wonder and discovery. Imagine, if you will, a time before time existed. There was no space, no matter, no energy as we know it. And then, 13.8 billion years ago, something extraordinary happened. An event that would set the stage for everything we know and love, everything we can see and touch, and everything beyond. This event was not an explosion in space, as is often depicted, but rather an expansion of space itself. It was the birth of our universe, a moment we call the Big Bang. In the blink of an eye, the universe went from an infinitely small and dense point, a singularity, to an unimaginably hot and rapidly expanding cosmos. From this primordial soup of energy, the building blocks of our universe began to emerge. In the first fractions of a second, the universe underwent a period of rapid expansion, known as cosmic inflation. This rapid expansion smoothed out any irregularities in the early universe, leading to the remarkably uniform cosmos we observe today. As the universe expanded, it cooled, allowing for the formation of the first subatomic particles. Quarks and gluons, the very essence of matter, combined and recombined, setting in motion the chain of events that would eventually lead to the formation of stars, galaxies, planets, and ultimately, life itself. In the first fleeting fractions of a second after the Big Bang, the universe was a place of unimaginable heat and density. It was a realm where the laws of physics as we know them were still being written, a time of chaos and rapid change. Yet within this maelstrom, the seeds of our universe were being sown. One of the most significant events of this early period was cosmic inflation. Imagine a balloon with tiny dots drawn on its surface. As you inflate the balloon, the dots move farther apart. Similarly, during cosmic inflation, space itself expanded faster than the speed of light, stretching the fabric of the universe and smoothing out any wrinkles or irregularities. This rapid expansion had a profound impact on the fate of the universe. It ensured that the universe would be relatively uniform on large scales, explaining why we observe a similar distribution of galaxies in all directions. It also stretched out any initial quantum fluctuations, creating subtle variations in density that would later serve as the seeds for the formation of stars and galaxies. The inflationary epoch lasted for only a tiny fraction of a second, but it played a crucial role in shaping the universe as we know it. It transformed a chaotic and disordered state into a vast and surprisingly smooth cosmos, setting the stage for the emergence of structure and complexity in the billions of years to come. As the universe continued to expand and cool, the primordial soup of energy began to condense into matter. This marked a critical transition in the universe's history, a time when the fundamental forces of nature as we know them began to emerge. Imagine a symphony orchestra tuning their instruments before a performance. At first there's a cacophony of sound, but then, slowly but surely, harmony emerges as each instrument finds its proper place. Similarly, in the early universe, the four fundamental forces, gravity, electromagnetism, the weak force and the strong force, began to separate and take on their distinct characteristics. Gravity, the force that governs the large-scale structure of the universe, was the first to emerge. Then came the strong force, responsible for binding quarks together to form protons and neutrons. The electromagnetic force, which governs the interaction of light and matter, and the weak force, which plays a role in radioactive decay, also emerged during this period. The emergence of these fundamental forces marked a turning point in the universe's evolution, as it set the stage for the formation of atoms, the building blocks of all ordinary matter. Approximately 380,000 years after the Big Bang, the universe had cooled enough for electrons to combine with protons and neutrons, forming the first atoms. This event, known as recombination, had a profound impact on the universe, as it allowed light to travel freely for the first time. Before recombination, the universe was a hot, dense plasma where photons, or particles of light, were constantly scattering off free electrons. It was like trying to see through a thick fog. But once electrons were bound into atoms, the fog lifted, and the universe became transparent. The light that was released at this time has been traveling through the universe ever since, carrying with it a snapshot of the universe as it was in its infancy. Today, we can still detect this ancient light, known as the cosmic microwave background radiation, or CMB. It's a faint glow that permeates the universe in all directions. The CMB is a treasure trove of information about the early universe. By studying its subtle temperature variations, cosmologists can learn about the universe's age, composition, and geometry. It's a remarkable testament to the ingenuity of scientists that we can peer back in time and observe the universe as it was billions of years ago. For millions of years after recombination, the universe remained a relatively dark and quiet place. The only light came from the faint afterglow of the Big Bang, the cosmic microwave background radiation. But beneath this seemingly tranquil surface, a dramatic transformation was brewing. Gravity, the architect of the cosmos, was at work, slowly but surely drawing together vast clouds of hydrogen and helium gas. These clouds, remnants of the Big Bang, were the seeds of the first stars and galaxies. As gravity pulled them together, they began to collapse under their own weight, heating up and becoming denser. Finally, after millions of years of contraction, the cores of these collapsing clouds reached temperatures and pressures high enough to ignite nuclear fusion. Hydrogen atoms fused together to create helium, releasing enormous amounts of energy in the process. The first stars were born, brilliant beacons of light that pierced the darkness of the early universe. This era, known as the Cosmic Dawn, marked a pivotal moment in the universe's history. The first stars were not only sources of light, but also cosmic engines that would shape the universe for billions of years to come. The first stars were colossal giants, hundreds of times more massive than our Sun and millions of times brighter. They lived short, intense lives, exhausting their nuclear fuel in a few million years. When these stellar behemoths reached the end of their lives, they exploded as spectacular supernovae, seeding the surrounding space with heavier elements. These stellar explosions played a crucial role in the formation of galaxies. The shockwaves from supernovae compressed nearby clouds of gas, triggering the formation of even more stars. Over time, gravity drew these stars together into vast, rotating collections bound together by their mutual gravitational attraction. The early universe was a chaotic place, with galaxies colliding and merging in a cosmic dance of creation and destruction. These interactions fueled the growth of galaxies, shaping them into the diverse array of shapes and sizes we observe today. From the graceful spirals of galaxies like our own Milky Way to the massive elliptical galaxies that dominate galaxy clusters, each galactic island tells a unique story of cosmic evolution. As billions of years passed, the universe continued to expand and evolve. Galaxies clustered together, forming vast cosmic webs with enormous voids separating them. Within these galaxies, new generations of stars were born, lived out their lives and died, enriching the interstellar medium with heavier elements. Our own Milky Way galaxy, a barred spiral galaxy some 100,000 light-years across, is just one of billions of galaxies in the observable universe. It's home to hundreds of billions of stars, including our own Sun, a relatively ordinary star located in one of the Milky Way's spiral arms. The universe we observe today is a testament to the power of gravity, the elegance of physics, and the incredible scale of cosmic time. From the first faint glimmer of starlight to the majestic tapestry of galaxies that stretches across the cosmos, the story of the universe is a story of constant change, evolution, and the emergence of complexity from simplicity. Galaxies, it turns out, are not randomly scattered throughout the universe. Instead, they tend to congregate in vast groups, much like islands clustered together in an archipelago. These gatherings of galaxies are called galaxy clusters, and they represent some of the largest structures in the cosmos. A typical galaxy cluster can contain hundreds or even thousands of galaxies, all bound together by their mutual gravitational attraction. These clusters are filled with not only galaxies, but also hot X-ray emitting gas and a mysterious substance known as dark matter, which we'll delve into later. But the cosmic organization doesn't stop there. Galaxy clusters themselves are often grouped into even larger structures called superclusters. These colossal assemblies can span hundreds of millions of light-years and contain thousands of galaxies, making them some of the most massive objects in the observable universe. Our own Milky Way galaxy is part of a relatively small group of galaxies known as the Local Group, which, in turn, is part of the Virgo supercluster, a massive collection of over 100 galaxy groups and clusters. If we could observe the universe on the grandest scales, we would see a remarkable pattern emerge, a vast, intricate network of galaxies, gas, and dark matter known as the cosmic web. This web-like structure is the result of billions of years of gravitational evolution, as matter in the universe clumped together under its own weight. Imagine a spiderweb glistening with dew in the early morning light. The filaments of the web represent the dense regions where galaxies cluster together, forming long, interconnected strands that stretch across billions of light-years. These filaments are thought to be tracing out the underlying scaffolding of dark matter, which forms the gravitational backbone of the cosmic web. In between these filaments lie vast, relatively empty regions known as cosmic voids. These voids, some of which can be hundreds of millions of light-years across, are not entirely empty, but they contain far fewer galaxies and less matter than the filaments. The cosmic web is a testament to the interconnectedness of the universe, where gravity has woven a complex tapestry of structure on scales that dwarf even the largest superclusters. While we can observe the luminous matter in the universe, such as stars and galaxies, there's a hidden component that plays a crucial role in shaping the cosmic web dark matter. This mysterious substance doesn't interact with light, making it invisible to our telescopes, but its gravitational influence reveals its presence. Dark matter is thought to make up about 85% of the matter in the universe, and its gravity is believed to be responsible for the formation of the large-scale structure we observe. In the early universe, dark matter's gravity acted as a seed, pulling in normal matter and forming the first clumps that would eventually grow into galaxies and galaxy clusters. Without dark matter, galaxies would likely not have formed as early or as efficiently as they did, and the cosmic web would be a much less intricate and interconnected structure. Dark matter's invisible hand has shaped the universe we see today, from the largest superclusters down to the individual galaxies that populate them. It remains one of the most profound mysteries in modern astrophysics, and its true nature continues to intrigue and challenge scientists. In the vast expanse of the cosmos, amongst the billions upon billions of galaxies, lies our own celestial island, the Milky Way. This swirling city of stars, gas and dust is our galactic home, a place of wonder and beauty that has captivated humankind for millennia. To the naked eye, the Milky Way appears as a faint luminous band stretching across the night sky, a river of light flowing through the celestial tapestry. This ethereal glow comes from the combined light of billions of stars, too faint to be seen individually, yet together creating a breathtaking spectacle. But the Milky Way is far more than just a pretty sight. It's a dynamic and complex structure, a swirling vortex of stars, gas and dust, all held together by the invisible hand of gravity. It's within this galactic metropolis that our own solar system resides, a tiny speck orbiting around a rather ordinary star we call the Sun. Like many galaxies in the universe, the Milky Way is a barred spiral galaxy, its structure resembling a giant cosmic pinwheel. At its heart lies the galactic bulge, a dense region packed with stars, gas and dust. This central hub is thought to harbour a supermassive black hole, a gravitational monster millions of times the mass of our Sun. Emanating from the central bulge are the Milky Way's majestic spiral arms, vast streams of stars, gas and dust that swirl around the galaxy's centre. Our solar system resides in one of these spiral arms, known as the Orion Arm, located about 2/3 of the way out from the galactic centre. Surrounding the galactic disk, which contains the spiral arms, is the galactic halo, a vast spherical region populated by older stars, globular clusters, and a mysterious substance known as dark matter. This halo is thought to be a relic of the Milky Way's formation, containing stars that were born in the early universe. The Milky Way, like most galaxies, is not a static island in space, but rather a dynamic and evolving structure, constantly shaped by its interactions with its surroundings. One of the ways in which galaxies grow and evolve is through a process known as galactic cannibalism, where larger galaxies consume smaller ones. Over billions of years, the Milky Way has pulled in and absorbed numerous smaller galaxies, merging with them and incorporating their stars, gas and dust into its own structure. These mergers have left their mark on the Milky Way, creating streams of stars in the galactic halo and influencing the shape of its spiral arms. Currently, the Milky Way is in the process of merging with a dwarf galaxy known as the Sagittarius dwarf galaxy, which is being stretched and distorted by the Milky Way's gravity. In the distant future, the Milky Way is destined for a more dramatic collision with our nearest large galactic neighbour, the Andromeda Galaxy. While galaxies engage in their cosmic dance across the universe, within their swirling arms, even more profound events are unfolding. In the outskirts of the Milky Way, some 4.6 billion years ago, a cold, dark cloud of gas and dust, a nebula, began to collapse under its own gravity. This particular nebula, perhaps nudged by the shockwave of a nearby supernova, was destined to become the birthplace of our solar system. As the cloud contracted, it began to spin faster and faster, like a figure skater pulling in their arms. This spinning motion caused the cloud to flatten into a rotating disk, with most of the material concentrated at the center. At the heart of this swirling disk, the temperature and pressure continued to soar as gravity relentlessly pulled more and more material inward. Finally, the core of the collapsing cloud reached a critical threshold, igniting nuclear fusion. Hydrogen atoms, crushed together under unimaginable force, fused to form helium, releasing a tremendous amount of energy in the process. Our Sun, a newborn star, blazed to life. While the Sun was igniting at the center of the collapsing cloud, the remaining gas and dust continued to swirl around it in a vast rotating disk known as a protoplanetary disk. This disk, stretching out for millions of kilometers, was the chaotic nursery where planets would eventually form. Within the disk, tiny particles of dust, remnants of ancient stars, began to collide and stick together through electrostatic forces. These tiny clumps, no bigger than grains of sand, marked the very first step in the planet-forming process. Over millions of years, these clumps grew larger, forming pebble-sized objects, then boulder-sized, and eventually kilometre-sized planetesimals. The protoplanetary disk was a chaotic and violent place, with planetesimals constantly colliding, shattering, and sometimes merging together in colossal impacts. These collisions played a crucial role in shaping the destiny of the planets, determining their size, composition, and ultimate fate. Over millions of years, the planetesimals in the protoplanetary disk continued to collide and grow, eventually forming the planets we know today. The inner region of the disk, closer to the Sun, was hot and dry, with only rocky materials able to withstand the intense heat. This is where the inner rocky planets, Mercury, Venus, Earth and Mars, formed. Further out in the disk, beyond the so-called frost line, temperatures were cold enough for volatile compounds like water ice, methane and ammonia to exist in solid form. These icy materials, along with vast amounts of hydrogen and helium gas, provided the building blocks for the giant planets: Jupiter, Saturn, Uranus and Neptune. The giant planets, with their immense gravity, swept up vast amounts of gas and dust from the surrounding disk, growing to enormous sizes. Jupiter, the largest planet in our solar system, is more massive than all the other planets combined. These gas giants played a crucial role in shaping the architecture of the solar system, influencing the orbits of the inner planets and shaping the distribution of asteroids and comets. Our journey through the cosmos has taken us from the universe's fiery birth to the intricate formation of galaxies, stars and planets. We've witnessed the universe's incredible expansion, the emergence of structure from chaos, and the delicate dance of gravity that shapes the cosmic landscape. From the smallest atom to the largest supercluster, the universe operates according to a set of elegant laws. Laws that govern the motion of celestial objects, the interactions of particles, and the flow of energy. These laws, deciphered through centuries of scientific inquiry, reveal a universe of breathtaking order and complexity. As we reflect on this cosmic chronicle, we're struck by the vastness of space and the immensity of time. Our planet, our solar system, even our galaxy are but tiny specks in the grand scheme of things. Yet, within this vast and ancient universe, life emerged on our planet, a testament to the universe's remarkable capacity for complexity and self-organization. The realization of our place in the universe can be both humbling and awe-inspiring. We are, in a very real sense, children of the cosmos, our very existence intertwined with the universe's grand narrative. The atoms in our bodies were forged in the hearts of stars. The molecules that make up our cells were once part of ancient nebulae, and the energy that sustains us comes from the nuclear fusion reactions taking place in the core of our sun. As we strive to understand the universe, we also come to understand ourselves better. The study of the cosmos is not merely an academic pursuit, it's a journey of self-discovery, a quest to uncover our origins and our place in the grand tapestry of existence. And as we gaze up at the night sky, filled with the light of distant stars, we're reminded that we are connected, not just to our planet and to each other, but to the universe itself. We are part of something much larger than ourselves, a cosmic story that began billions of years ago and continues to unfold today. The story of the universe is not a finished tale, but rather an ongoing epic, with new chapters being written all the time. The universe is constantly expanding, evolving, and revealing new secrets to those who seek to understand its mysteries. As we continue to explore the cosmos with increasingly powerful telescopes and sophisticated instruments, we can expect to make even more astounding discoveries. We may uncover the true nature of dark matter and dark energy, unravel the mysteries of black holes, and perhaps even find evidence of life beyond our planet. The universe is full of wonder, beauty, and endless possibilities. As we continue our exploration of the cosmos, we can be sure that the universe will continue to surprise and inspire us, revealing new wonders and challenging our understanding of the cosmos and our place within it. The Cosmic Chronicle is far from over. In fact, it's just beginning.